Hello students, welcome back. I hope you are doing good. So in this part, we will discuss about your Avogadro's law and your ideal gas equation and your Graham's law of diffusion. So let's start with our part. Next law, Avogadro's law. Avogadro's law gives you an idea between your volume occupied by number of moles. For example, consider a cylinder. In the cylinder, what I am doing is now, it is filled with 100 gas molecules, which is the maximum capacity of this cylinder. So maximum capacity of this cylinder is 100 moles. Now, I want to add extra 50 moles to this cylinder. So what are the options I have? I have that if I increase my volume, if I take my piston from this position to this position, what is happening? My volume is increasing. Then if my volume increases, I can accommodate remaining 50 moles of a gas. So here my volume is simultaneously increasing if I increase my number of moles from 100 to 150. So my volume is directly proportional to the number of moles of gas. So obviously you need a constant, right? If there is any proportionality, you need a constant. So my volume is nothing but it is equal to constant into n. So V1 by N1 is equal to V2 by N2. Remember guys, this is happening only at constant temperature and your constant pressure. So unless and until you know that your temperature is constant and your pressure is constant, you can't come to conclusion that my volume is directly proportional to my number of moles. So you can see here you can see that there are 3 moles of hydrogen, 3 moles of hydrogen reacts with 1 mole of nitrogen to give 2 moles of ammonia. And you can see the volume here, right? This is a very big volume. This volume is very big because there are 3 moles. This volume is minimum because there is 1 mole, that's it. This one is an intermediate between this one and this one, because this value itself, this value of the number of moles is intermediate in between this number of moles and this number of moles. So you can see the volume, the effect of volume on my number of moles. So my volume is directly proportional to my number of moles. So let's solve a question. Let's solve a simple question. So ammonia burns in oxygen to form nitric oxide and water vapor. How many volumes of nitric oxide are produced from 1 volume of ammonia at the same temperature and pressure? So the reaction is ammonia, it burns in oxygen. Ammonia burns in oxygen to give you your nitric oxide and water vapor. So what is the information given? What is the information known? The information known is that my 1 mole of ammonia gives 1 mole of NO, because 4 moles of ammonia gives rise to 4 moles of NO. So obviously 1 mole of ammonia will be giving rise to 1 mole of NO, right? So at the constant temperature and pressure, it is already given in the question that same temperature and pressure. So how many volumes of NO are obtained now? Obviously, since 1 mole of ammonia gives 1 mole of NO, 1 volume of ammonia gives rise to 1 volume of NO, right? So next important concept is ideal gas equation. So till now we have learned different laws. And what are the outputs of different laws? For example, pressure is inversely proportional to volume, which is Boyle's law. Volume is inversely proportional to pressure, or pressure inversely proportional to volume. Next, Charles' law. Your volume is directly proportional to temperature. And Avogadro's law, which says my volume is directly proportional to n. So guys, what is the important concept? Think about it. What is the important concept in all these 3 laws? What is the common factor in all these 3 laws? Just think for a few seconds. Yes, right? Volume is the common factor. Here volume is inversely proportional to pressure, volume is directly proportional to temperature, and volume is directly proportional to the number of moles. So I am fixing my volume and I am relating with different parameters like pressure, temperature, and number of moles. So now can I come to one conclusion? Can I come to this conclusion using these three equations? Yes, I can come to this conclusion. This conclusion is nothing but my volume is directly proportional to number of moles, my volume is proportional to the temperature, and volume is inversely proportional to pressure. That means my volume is directly proportional to the product of N and T, and it is inversely proportional to the pressure. Obviously, if there is a proportionality value, there will be a constant. Yes, here also you have a constant. So that volume is nothing but it is constant into NT by P. So I can say my volume is nothing but RNT by P, where R is a constant, which is nothing but a universal gas constant or gas constant. So this is very important equation in your gas laws, or this is a very important equation in your gaseous state, I can say, because this is a basic equation which will be useful for every calculation in gaseous state. So yes, PV is equal to nRT. I will take my pressure here and it will be PV, which will be equal to nRT. So the conditions at 0 degree centigrade and 1 atm, which is standard temperature and pressure. So what can I say? At 1 atm and 273 Kelvin, 0 degrees is nothing but what, guys? It is nothing but it is 273 Kelvin. So it is STP. So experiments show that at STP, 1 mole of any ideal gas occupies 22.414 liters. This is very important. At STP, 1 mole of any ideal gas occupies 22.414 liter. So since PV is equal to nRT and R is equal to PV by NT, here what is known? Here the value of volume is known. What is the value of volume? 22.414. The value of number of moles is known, which is 1, and the value of temperature is known, which is 273 Kelvin, and the value of pressure is known, which is 1 atm. So at STP, I can find the value of R. So R is nothing but 1 atm into 22.414 divided by 1 mole 273.15. So R is nothing but 0.0820, and R value is also written as 0.0821. It is approximately equal to 0.0821. Remember one important thing here, that my unit of volume is in liter, my unit of volume is in atm. So if I take my value of unit of volume in liter and unit of pressure in atm, then only I can say that my value of R is 0.0821. For example, if you take my value of volume in meter cube, and if you take my volume of pressure in SI unit, which is Pascal, or if I take in kilopascal, my value of R will be different. So let's solve a question. So argon is an inert gas used in light bulbs to retard the vaporization of the filament. A certain light bulb containing argon at 1.20 atm and 18 degrees centigrade is heated to 85 degrees centigrade at constant volume. What is the final pressure of argon in the light bulb? So here you are given the information about what? You are given the information about pressure, you are given information on temperature, and volume is constant. Remember this point. So temperature is getting changed, temperature is increasing from 18 to 85. So what should happen to pressure? Think about it, guys. Yes, temperature is increasing, volume is constant, so my pressure should also increase according to PV is equal to nRT. So nR by V is a constant, so P will be directly proportional to temperature. PV is equal to nRT, N, V and R are constant. nR by V is nothing but P by T, which is a constant. So I can say that P1 by T1 is equal to P2 by T2. So all the information is given, P1 is given, T1 is given, P2 is to be found and T2 is given. So P2 is nothing but P1 into T2 by T1, which is nothing but 1.20 into 358 by 291, which is 1.48 atm. So you can say that my temperature is not only proportional to volume, but my pressure is also directly proportional to, my temperature is also directly proportional to pressure, keeping your volume constant and also the number of moles constant. Now, we can calculate one important factor, density, from ideal gas equation. What is density? Density is nothing but mass by volume. And what is mass? Mass is nothing but, it is related to what? Mass is nothing but number of moles into its molecular weight. But what is volume? Volume is nothing but nRT by P. So when I divide mass by volume, so it will be N into M by nRT by P. So it will be P goes to the numerator, it will be Pm by RT. What is P? P is the pressure, R is the universal gas constant, T is the temperature and M is the molar mass of the gas. So my M will be what? M will be rho RT or dRT by P. So this is a question. At which of the four conditions the density of the nitrogen will be largest? So using the previous concept, you have to tell at which of the four conditions the density of nitrogen will be largest. A at STP, B at 273 Kelvin and 2 atm, C 546 Kelvin and 1 atm, D 546 Kelvin and 2 atm. Think about it for a while. Think about it, how to calculate. So you know that density is what? Pm by RT. So use this concept. So the interesting fact you can find here is that here M by R is a constant for all of this, right? For A, B, C, D, all this, M by R value is constant. So my density will be depending on the ratio of P by T. So higher is the value of P by T, density will be the maximum. So what is STP? It is 273 Kelvin and 1 atm. What is B? 273 Kelvin by 2 atm. So the numerator value is increasing. What is C? Here the denominator value is increasing, right? 546 and 1 atm. And what is D? It is 546 by 2 atm. So density of the gas is nothing but Pm by RT. So obviously the choice that has a greater value would be what? Since here the numerator value will be more, so it will be 2 by 273, which is the maximum of all the options available. So the answer B is the correct answer because P by T ratio is maximum. So obvious choice will be B. So next important law, Dalton's law of partial pressures. So you can see here there is a red molecule, here you can see a green molecule, here you have a red molecule as well as green molecule. So I am combining both this to give this. So obviously red molecules exert a pressure P1, green molecules exert a pressure P2. Both red and green molecules exert a pressure P1 and P2. That means, and if I combine all these gases, the total pressure will be P1 and P2. And remember, I have to keep my volume and temperature constant. Here my temperature and volume both are constant. Only thing is varying is pressure. So consider in case A, two gases, obviously A and B, obviously they take the shape of the container, that means the volume is V. So this volume is V. So what do you know? You know that pressure is nothing but Na RT by V. How? From the ideal gas. From the ideal gas you will get it Na into RT by V. So N is the number of moles of A. Next, what is Pb? Pb is nothing but Nb into RT by V, which is nothing but the pressure exerted by B. Nb is the number of moles of B. And what is P total? P total is nothing but Pa plus Pb. Now let's solve a question. So a sample of natural gas consists of 8.24 moles of CH4, 0.421 moles of C2H6, 0.116 moles of C3H8. If the total pressure of the gas is 1.37 atm, what is the partial pressure of propane? So here it consists of the question. There are three types. One is CH4, C2, and second is C2H6, and third is C3H8. So what is given? The number of moles is given. So total pressure is also given. So total pressure is given, number of moles is given, and you have to find the partial pressure. So what is partial pressure? Partial pressure is nothing but mole fraction of the, for example, here I am asked the partial pressure of C3H8, right? So the partial pressure of C3H8 will be mole fraction of C3H8 into the total pressure. So what is the total pressure? The total pressure is 1.37 atm. So mole fraction of propane will be the ratio of number of moles. What is the mole fraction of propane? It is nothing but number of moles of propane, which is 0.116 by 8.24 plus 0.421 plus 0.16. This is the total number of moles. So mole fraction of propane will be the ratio of number of moles of propane to the total number of moles. So which is equal to 0.0132. So mole fraction of propane multiplied by the total pressure gives you the partial pressure of propane, which is equal to 0.0181 atm. Now, from the previous concept, we got a relationship between your partial pressure of any single gas in a combination of different gas, right? The pressure exerted or the partial pressure exerted by a gas molecules. Now, in this concept, in this slide, you will be learning about the concept related to the diffusion, or I can say Graham's law of diffusion. So now imagine, let's keep a race. Let's keep a race between two gases. For example, hydrogen and chlorine. So if it is a 1 kilometer race, this is 1 kilometer, and at the initial point there is hydrogen and there is chlorine. So now the race starts. Both hydrogen is running, chlorine is running, hydrogen is running and chlorine is running. Can you tell me which gas reaches the target line? Yes, hydrogen reaches first. Why? Because hydrogen reaches first because hydrogen is lighter in weight. Hydrogen is lighter in weight. So its mass is how much? Its mass is 2 grams. Chlorine, its mass is nearly 71 grams. So this is very, the hydrogen is having very less mass and chlorine is having heavy mass. So you can come to conclusion that lighter gases moves faster. So I can also say one thing, that I will add one more point, that the rate of diffusion of gases is inversely related to the square root of the molar mass. So if the molar mass is higher, my gases move slowly, or I can say my rate of diffusion is also slow. So you need a relation, right? Obviously all the concepts, all the laws are finally developed or analyzed based on a relationship or based on an equation. So this equation gives you an idea about the rates of diffusion and the molecular masses. So you can see here that my rates of diffusion is inversely proportional to square root value. So you can see a square root value here, right? So always remember guys, my rates of diffusion of gases is inversely proportional to the square root of its molecular mass. So Ma is the molecular mass of a corresponding A and Mb is the molecular mass of corresponding B. So you can see in this animation that, for example, you have HCl and NH3. If both the gas molecules here, both the gas molecules move at the same speed, and if they move at the same speed, what happens? Obviously they will meet at middle, right? Obviously if the speeds are same, they will meet at the middle, because distance is same, speeds are same, the time taken will be same, and if the time taken is same, they will be meeting at the center. But really, for example, if I introduce HCl at one end and ammonia at other end, will they meet at the middle? I mean, will the speeds are same? No, not at all. So you can see here, they meet towards HCl. They meet towards HCl because here you have to understand the same concept that HCl, what is the mass of HCl? HCl molecule mass is 35.5 plus 1, which is of hydrogen, it is 36.5. Ammonia gas is just 14 plus 3, 17. So obviously this gas will be moving faster. So this gas speed is high than this gas. So that means in a given time t, for example 10 seconds, in a given time 10 seconds, since you already know from Graham's law of diffusion that the lighter is the gas, faster it moves. So it moves faster and it crosses the half line benchmark, and it meets HCl near HCl side. So what is the reason? Lighter gas moves faster, and remember, it always meets closer to your heavier gas. So students, gas laws gives you an idea about what is happening to pressure and volume and temperature and number of moles of gas. And also you got the concepts of extra ideas like your Graham's law of diffusion. What is happening to the diffusion when two gases starts a race from one point, right? The lighter gas reaches the target first. This idea you get it from Graham's law of diffusion. So in this part you got the basic concepts, all other basic concept of your pressure, volume and temperature, the properties, the relationship between these parameters, right? So gas laws gave you overall idea about what is the relationship. I can mention this word relationship. So you are getting the relationship between the different parameters of gases, right? It was an interesting part. So in the next part, we'll go deep and we'll discuss about the kinetics. I mean kinetic theory of gases, right? So kinetic theory of gases gives you some more interesting ideas about your gases. So we'll discuss about this in our next part. So till then, keep tuned to our sessions. Take care of yourself. Goodbye.